Hello everybody, and welcome to the latest edition of the virtual Green Bank Observatory Colloquium series. I'm delighted to welcome our guest today, Anna Kapinska from NRAO, who will be talking with us about the Australian Emu radio survey. That's Emu, Evolutionary Map of the Universe. A beautiful acronym, if ever there was one. So let's please give her a virtual welcome. And if you have any questions during the talk, you are welcome to unmute yourselves and ask them, or you can save them for the end. But everybody, let's give it up for Anna.
Thank you, Jessie. And thank you for having me today. I wish I could be in person in Green Bank, but it's at times. So yes, today I'd like to show you our latest results, as well as update on the Emu radio survey. This is an Australian indeed survey with Australian Escape Pathfinder ASCAP that is beautifully in the background of this picture. Something that I actually got involved while I was doing my postdoc in Western Australia, and I've been involved with Emu survey for by now I think it's going to be 8 years, and it's finally reaching the start of the full survey. So it's great to see, and I stayed involved in it even after after joining NRAO as part of the exec of the team, but more on this later. So in this crowd, I'm pretty sure I don't have to introduce SKA itself, but I figured I'll put in one slide or two just with the kind of a little bit of history. I like kind of mentioning it because the SKA idea started like 3 decades ago, really, to build a new generation radio observatory. And since then, the SK organization had renamed, and I think it's just a very recent thing, to SK Observatory. And before the hosts were host sites were chosen, countries could, because this is an international, of course, project, the countries could bid for their location to be considered as the host. And Australia actually bid with very much building or planning, initially planning, but eventually building the Australian Escape Pathfinder ASCAP. Well, what really happened is that eventually, I think it was 2012 when the SKO decided that ultimately the SKO will be hosted by 2 countries, South Africa and Australia, and Australia got the lower frequency one. When you can see here, this is the artist's impression. They got a low frequency end, so something between 50 and 350 megahertz, while South Africa got the mid, around 1 to 10 gigahertz. But still, we ended up with a ASCAP radio telescope, which now became so actually has its own life. And as some of you might have seen the news from this week, and I think this is sort of also shows that finally SK is underway as of this week. And I love this this word finally, that it really shows that it's been years. And after 30 years of planning, the construction begins. So as far as I know, my colleagues were saying that they're all very much celebrating. But enough about that. Because Emu is the survey with ASCAP, let me just give you a very brief summary to have everyone on the same page, or introduce it to those that may be totally new. So this telescope, ASCAP, is located in a remote observatory, Murchison Radio Astronomy Observatory in Western Australia. It is a protected radio quiet zone, and it is around 700 kilometers or 800 kilometers, which would be 500 miles from Perth in Western Australia. You can see roughly this map where it's located. The telescope consists of 36 antennas, each 12 meters in diameter, and the maximum baseline is 6 kilometers. I think the minimum is 22 meters. The antennas are non-movable in the sense that there is no movable configuration, like for example with the VLA. And so if you want to change the configuration, you basically need to adjust your visibilities, as in you may want to remove, for example, the longest baselines, or adjust it with the weighting. ASCAP operates in the frequency range between 700 megahertz and 1.8 gigahertz, and that's there are 3 bands across this range. In each band has 288 megahertz instantaneous bandwidth. What's so very special about this telescope, and why it is really a survey radio telescope, is the new, the state-of-the-art receivers that are installed. They're called phase array feeds, or PAFs, and you can very much, I hope you can see my mouse. You can see this is the illuminated, that's where the PAFs are installed, and here you have a zoom in onto that. They are formed of, they are made up of 188 individual receivers. And thanks to that, it can up to like 36 independent but simultaneous beams on the sky can be formed at a time, and that very much enables to observe instantaneously a large field of view. And often what is quoted for a reference is that it's approximately 30 square degrees at 1.4 gigahertz. What it all says is that the telescope really is can scan the sky really, really, really fast, and that's why it's predominantly used for surveys, and as it is very much designed for it. Now, CSIRO quotes data rates up to 10 to 14 bits per second. That's a lot of data, and that's very much the bottleneck currently, is the data processing rather than the observation. And CSIRO also has dedicated supercomputing center for data processing because of that. Now, I will not go into details on the technical aspects of ASCAP or EMU itself. And for more on that, I will forward you to a technical talk on the ASCAP and EMU and PAFs, including by Josh Marvel, also from NRAO Socorro, that will be coming in the next year, probably February. So please keep an eye on that, and you can learn more about the more technical aspects of the telescope and survey itself. I will focus predominantly on the science and the results in this talk. So as for EMU, this is a continuum radio survey of the southern sky. The full survey specifications are, the main ones are as follows. It is, we decided that the full survey is going to be at 943 megahertz as a central frequency. We still do have this almost 300 megahertz bandwidth. And with that, the survey will reach 15 arcsecond resolution and noise levels of approximately 20 to 25 microjanskeys per beam. Now, how does it compare to what we currently have? It is going to be 30 times better than NVSS, approximately 10 times better, or maybe slightly less than that, better than Villas. And it is comparable to LOFAR, if you scale it accordingly, because I think LOFAR is around 80 microjanskeys at a much lower frequency. Even though I said it's a southern sky, the plans are to map the sky up to plus 30 degrees in declination. Maybe plus 20, we will see how that thing, how it goes, but definitely into positive declination regions. And if we go to up to plus 30, the estimate is that we will be detecting something like 30 million sources The Emu strength, apart from being super fast, also lies in the superb surface brightness sensitivity that it has, or ASCAP has itself, and that is really nearing the confusion brightness limit. Emu is focused on Stokes eye, but of course, the observations are designed in to record also the polarization, the full polarization information, but the polarization aspect of these observations are covered by POSSUM polarization POSSUM survey, which is the polarization survey, and it's commensal to Emu very much. They are piggybacking on us. And I will not discuss POSSUM as it is a separate team that it's dealing with that. So I'll be focusing only on Emu and the Stokes eye here. So by now, early science and pilot surveys have been performed, and we went through a different various of periods of that, from the science verification period in 2016 through the early science and 2 sets of pilot survey. There were a number of science papers coming out of these data. I mentioned here a few data releases that were associated with these periods, and these data are available at the quality and the formats that Emu eventually have. Now, I am also very, very happy to declare that the full survey has now started as well, as of something like 3 weeks ago. I think the first tiles were observed around 16th November 2022, and I'll flash a few of those by the end of the talk. Okay, since I will predominantly the science part in the talk that I'll move on to shortly is very much focused on the pilot data. Let me show you what the pilot observations covered. These are beautiful quick look maps made by Josh Marvel. The yellow tiles are the ones that were covered by pilot surveys. The red one is very much anticipated full survey tiles, and the cyan is where the individual beams within the tiles are. So when each of the tiles is 30 square degrees, then each of these tiles has that many 36 or so beams in it. And that's very much how it is covered. Now, by now, of course, we also have the plans for the full surveys since it has started. And in the first 5 years, so started just now up until end of 2026, the plan is to have it covered up to, I think, roughly equatorial levels, and the further north will be covered after that 5-year initial period. But again, please keep an eye on the technical talk on ASCAP and Emu by Josh Marvel in February to talk more about that. And by then we also will probably have an update on how the survey is progressing. All right, so this is one of the new generation radio facilities, and so the new generation radio surveys and so on. Now, everyone is really looking forward to those and the new discovery space. So the question is, what is there still to discover? And of course, there are things that we are awaiting, and these are the lower flux density limits of the surveys, going through, I mean, seeing finally the radio acquired AGN, for example, population of already the radio loud AGN, but at the lower luminosity levels and much higher redshifts. Of course, AGN EOR, as well as the star forming galaxies into much higher redshift that it has been possible so far. And then looking into the star formation history, finally, that we can go beyond the redshift of a few. And while all of it is really, really anticipated, the EMU itself is covering all of the science, really, starting from the closest, the galactic plane and galactic sensor, to the AG and in EOR, and going through star formation galaxies, AGN and clusters, and so on and so forth. But we have always been sort of aware that there may be other things that may come up to us and in this data, and we need to be sort of prepared for that. And the question is, how do we prepare for that? And this is the sort of unknowns. That is, there are the things that we don't know that we may discover. And while there were a couple of people that were definitely really looking forward to that, and really trying to come up with ideas how to look for these unexpected discoveries, how to prepare for that, I don't think anyone actually expected that this sort of discoveries will come super early on, even in a pilot survey of EMU. And so let me move on from this very plain slide to something that I want to focus on a little bit right now. And this is something that you may have heard of over the past couple of years, because it took media by a storm. We discovered in a pilot survey something that we called the odd radio circles, and so ORCs, just because scientists love their acronyms. And let me take you through this slide slowly. So what we actually did see in our pilot data from EMU is this sort of features, like this one or this one. This is a different, this is GMRT. I'll get back to you to it in a second, but these things started popping up. We did find initially just 3 of them, and these are all 3, and this is 1, this is number 2, and number 3 is this. If you can kind of see in the noise, I will show you in a second that actually it's real. And the EMU pilot 1 fields were approximately 270 square degrees. Now, this has been published in Norris and et al. In 2021. Now, why? Well, actually, the whole discovery came quite interestingly, because I did find the first one. I think it was one of those. I think it was this one. In the first, I think, couple of weeks of just staring at the data when they came out of the telescope from the for the pilot survey 1, and then completely independently to other people found. I think this one was refound, and this one was a new one in the following within the following month or so. So we had 3 people independently finding them and just looking, it's like, well, what the heck is that? And when then after that, we went through the whole analysis, what it possibly can be. One of the colleagues, Haub in Tema, also joined and basically said, well, look, I can also see that in a GMRT, and this is an example. This is what we called work number 4. It was found in archival GMRT data at 325 megahertz, and that was one of the cluster fields. The other 2 are EMU. So these are the these are the radio images, and the images on the right are the EMU contours, or GMRT in this case, overlaid on the DES image. DES stands for the Dark Energy Survey, and that was very much a plan from the start that EMU Pilot 1 would cover an area that is was observed with DES, so that we do have this optical counterparts to our observations. So that's what we found. We started looking at those and thinking what they potentially can be, but it was just not really straightforward what they can be. I put here what their spectral index is, because that will be relevant a few slides down the road. And very much they are steep spectrum sources. So from minus half to minus 1.7. And so the general spectral indices are very much average, sorry, over the source, and this one has minus 0.1, 0.2. This one is minus 0.8, which is the standard really canonical synchrotron emission, and this one is rather flatter at minus 0.5. Now you have a separate sources here. So this is a source S. This is a very highly very steep. It's minus 1.7, and you have here another one. This one is a flat spectrum source. This one is also fairly flat, and this one is steep. It's unclear whether these two are actually connected to this source at all. All right, so if you look a little bit in more detail, the ORC number 2, and this is just to show you which one it is. We had an ATCA follow-up observations of that one. And so this is this one. This is 2.1 gigahertz. And of course, ATCA is not amazing in the surface brightness sensitivity. So you don't have that all diffuse emission information, but that gave some sort of, well, we were hoping that it gives us some sort of perhaps confirmation or not, or maybe upper limit for the spectral index over the wider end of a wider range of frequencies. But it actually did detect the ORC number 2, which is this prominent circle here. If you can see, it's very very faint, and it is likely that it would be missed again, because it is I actually don't remember whether it has what is the significance of that, but because we know from ASCAP that it's there, we expect it to actually see that it's sort of confirmed that's a real source. This fluff is very much beyond the detection limit, so it's not in ATCA. Now on the left, to also look maybe in more of the diffuse emission of the source is these are Emu data, where the green one underneath is very much this image, the original from Emu, and the red one is in the Emu image that is filtered, it has filtered small scale features, and this is a method of Larry Rudnick, and it's published in 2002, and I would forward everyone to that paper to see the method, as I'm not really an expert on that one. But the moment you filter the small scale features and you start looking at the diffuse emission, this is very much what you get, and that what we called ORC3, that it's just a sort of hinted over here, it becomes much more prominent. Excuse me. So we also looked at the ORC number 1 in more detail. This one was a follow-up with Meerkat. I have not been unlike all the other things, I have not been very closely involved in the Meerkat follow-up on that one, but I figured that I'll show you that because it's very relevant. So this one, immediately after, I know that we were going for the Meerkat observations of one of the ORCs, and it was chosen to go for the ORC 1. I was in 2021. That was through the DDT, as far as I know, I think. And the Meerkat basically provided higher angular resolution observations and much deeper. And you can see that we did, so with the Meerkat, we did get it at 1.3 gigahertz, but the bandwidth is really amazing. It's 0.8 gigahertz bandwidth there. The resolution is very much twice as good. So you're looking at 6 arc seconds, and it's very deep. 2.4 microjanskis per beam, and you have side here the Meerkat and the ASCAP, how this source looks like. So it is also seen with other telescopes. So again, it is very much a real feature. And while you have this beautiful fluffy circular thing in ASCAP, Emu image, the Meerkat really starts showing you much more structure going on. And if you do go to that paper, there's more discussion going on that, and what sort of potential kind of a circular forms features that maybe just superimpose here on each other, but they may be in 3D. I just flashed through some sort of all the details that this source, like all the details that were investigated for the source with Meerkat. And again, I was not hugely involved in this particular paper, but I thought it is sort of important for the interpretation that I will show you in a second. I will discuss in a second to show you those. So again, this is the Emu and Meerkat, how that would look like on just a plain grayscale. But what the team there of Rai and his students looked at is the spectral index, and you can see that it is very much very steep. Even if you consider that being fairly in the noise, you're looking at least minus 1.1 and steeper than that. It is fairly highly polarized. This is this image that very much shows you that's in at least again in tenths of % on the fractional polarization. And they also looked into a more on the polarization side. This is the B vectors that are overlaid over the total polarized intensity image. That's one here. And analyzing all of it, this sort of came down to a 3 potential explanation of what these sources might be. But before I get there, let me actually go through all the possibilities we started off with the very first moment we found them, before we had the ATCA, or actually no, we did have already ATCA follow-up, but we didn't have the Meerkat yet. So as I said, this discovery caused huge media frenzy. Really, it is still being picked up even a year after the announcement, and also there is probably a lot of material up there in the wild web that was created even without our sort of knowledge, just because certain science pages were very, very keen on showing that off. So when we first discovered them, we started thinking, okay, so what are they? So the first thing is that either even real, or maybe that is some artifact from the telescope that is very much rejected simply because they are seen by other telescopes. There's GMRT, there is Meerkat, there is ATCA that also see them. So not only even Australian telescopes, but also the Indian and the South African. Scientifically then, these are all the possibilities we thought of, like supernova remnants. But both supernova remnants and the planetary nebula, they basically are far from the galactic plane. The field we found these orcs in were at a declination minus 65, minus 60. It's really, really far. And for the planetary nebula, also the spectral index was very much too steep. An option was, well, what if it is ring of the Wolf-Rayet star? Okay, if we forget about the galactic plane, for the Wolf-Rayet star, these are very much too large. They are, you know, a lot of these options require here that I listed require the features, or previously detected features, were few arc seconds in diameter, while we here looking at the resolution of 1411 or 14 arc seconds. So they are much, much, much larger sources. And for the ring of the Wolf-Rayet star, yeah, this is very much too large for it, and also the spectral index is too steep. An option was that what if it is a edge-on star-forming galaxy with some sort of wind, or it's a ring-type star-forming galaxy. But the thing is that apart from the GMRT orc that has the central coincident counterpart, it doesn't. The other 3 do not. And then how do the ring-type star-forming galaxy look like in Emu? This is the example. This is 693 NGC 6935. This is very much known, and you may argue that they are much more circular and regular than what we see, what we observe in the orcs, which are more irregular, even though it has this circular shape. We also consider like terminal shock of galactic wind. That's still theoretical possibility. there is some discussion in the paper in 21 when we say that it's possibility, but we're not convinced. Other two things could be cluster halo or Einstein ring. But the thing is that for either of these, the structure is too regular and there are no really galaxy clusters or any massive source for the gravitational lens. So of course, there we have also option of bent-tailed radio galaxy or lobe of the radio galaxy. These were very much on cliquey. That was always a possibility. And with the Meerkat follow-up observation, very much what it excluded a lot of these things. And the three options that we are left with is that it is indeed either a lobe of radio galaxy viewed end on, but not a blazer. Which basically is the case when you're looking down the jet directly. It could be a spherical shell from a starburst termination shock in starburst galaxy in the past, from the past events, or it could be a shock from some cataclysmic event such as merger of two galaxies. These are very much options that could not be excluded based what we found. And if you actually go onto the ADS, for example, and check, there is now a series, I think there's a series of follow-up papers, and some people still claim that it might be potentially supernova remnant, but I leave you that. If you're interested, please go and check the follow-up papers, the other papers that came after the first announcement of finding these things. And so, so this is what I wanted to very much briefly discuss with you. I'll show you the first unexpected thing that we found in the survey, something that well, maybe not, it's not necessarily spectacular new physics in there, but definitely a type of source that has not been seen in the radio surveys before. And we very much bring it down to the fact that the previous surveys did not have, when they had a resolution, they did not have enough of the surface brightness sensitivity to really detect these sources. And if they did have the surface brightness, although probably unlikely, the resolution would not very much show you that what really it is. And this is the new facilities that provide this high resolution and very deep imaging with a very good diffuse emission detection capabilities. So we're likely to see more of these type of sources, as well as other unexpected discoveries in this area of the discovery space. Okay, so let me now talk a little bit about the synergies between the Emu, which is still Australian source, even though the team is amazingly international, spanning at least 4 continents. But these are the synergies with the NRAO, and I say one is good, but 2 are much better. And what I'm really talking here about is very much a synergy between Emu and Villas. Now, this is something that is very much anticipated by many teams, including Emu, which is international, CIRADA collaboration, which is Canadian, Radio Galaxy Zoo, and many others. And why is it so? So even though Emu is the southern hemisphere survey and Villas is the northern one, they overlap in declination range. Villas definitely goes to -40 degrees, and we do have observations already at hand of those. And while Emu is expected to go up to +30, but if it doesn't go even that far, it will definitely be up at least the declination 0. So you're looking at either, in the best case scenario, 70-degree declination strip that these two surveys are going to be overlapping in, or at least 40 degrees. Either way, it's a very large overlap area. Now, to recap, Villas is a 2.1 gigahertz survey, and it has around 2 to 3 arcsecond resolution. The RMS, well, currently we're looking below 200 microjenskis per beam, but we are with the quick look imaging, and it will be much better than that once we have more of the single epoch imaging that has already started as well. This survey is ongoing, and observations will end in late 2024, but there's still a lot of data to process. So while the quick look imaging are coming up quickly, it will take a little bit longer for the final full science ready images, quality images to be out there. Emu, just to again recap, is 900 is below 1 gigahertz. Its resolution is 5 times worse, but the RMS is the sensitivity is much higher. We're looking at something like 20 microjenskis per beam. This survey just started, and the observations and data processing will be incremental over the next 5+ years, but very much I think we can anticipate, unless something really weird happens, that most of the anticipated footprint coverage will be released by 2028. So they are very much kind of they go hand in hand, Villas and Emu, with the data availability. And I just put it here as a comment that Meerkat is unlikely to perform a full sky survey simply because it will take years and years and years. But it will have deeper, just smaller area surveys out there. So to give you an example how that overlap look like and why is it so extremely useful, as these two surveys have different strengths. I put on together Emu pilots and Villas quick look imaging in one of the fields that overlapped, because we do have a couple of fields like that. And very much I did here this RGB true color image when I only use red and blue. But hopefully you can see, so the blue one is the Emu pilot. The resolution of that one is the native resolution without we convolve to the common one, which is 14 times 11 arc seconds. And you can, I just zoomed in so you can see it in detail. You can see that in Emu, we can see this these radio galaxies, which have this beautiful extended tails. Now in red, this is the Villas quick look. So it still has some side lobes, and but that's not the point here. In this particular image, it's more about the resolution and what sort of information it gives you. So for example, this double blob, it clearly is resolved in Villas into a beautiful double lobed radio galaxy where you can pinpoint where the core is, and very much how the lobes look like in more detail. You can pinpoint the cores, and that is extremely useful in finding the counterparts and then and then estimate if being able to match it with the multi-wavelength data, getting redshift and so on and so forth. I found this one actually quite interesting as well, because while it looks like some sort of band radio galaxy in Emu, one could probably figure that it's somewhere here is the core. Villas really, it tells you that the core is over here. And interestingly, this blob, this is actually has even own internal structure. So while Villas does not say these diffuse tails, which are also very important if one studies, in this particular case, for example, the physics going on and the mixing of the jets and the lobes with the external medium, it does tell you a lot about the compact structures in this sources. So that's why it is very highly anticipated. A lot of people are waiting for that, and some of the work can already be done. But of course, even for the pilot Emu, ideally we would have the Villas single epoch that are ongoing. I'm just marginally involved in Villas, but I am still as well. So I keep an eye on that, and as well as the I'm involved more on the quality of the imaging. So these are the extragalactic fields, and this is fantastic. But Emu is also Emu is also targeting a galactic plane and galactic center, very much galaxy, simply because we are in the southern, with Emu, we are in the southern hemisphere, so we have this fantastic access to that part of the sky. And very much what I wanted to show you in this particular image is the need for single dish observations. And I know this image is far from perfect, but I think it demonstrates the need very, very, very well. So this one is coming. These images are coming from a paper by Grazia Omana, also from last year, where we very much showed the first glimpse into a galactic plane observations from Emu. Again, as I'm saying, this is far from perfect, but there are two things here. One is that it needs better reconstruction, but as everyone or many people know, the galactic areas are the hardest to deconvolve, just simply because of the different the variety of different scales involved, and how bright it is. But you can easily see that there are lots of negative balls and so on and so forth. But to kind of give you a better view on this, how much improvement it is, despite all of this, that it's to be improved. This is an example also from the same paper, when we show the improvement in the resolution, and what it compares to is the Molonglo Galactic Plane survey with the Molonglo Observatory Synthesis Telescope, and how that particular source is now better resolved with ASCAP. This is the native beam, and you can see much more structures going on there. And this image is so much better than that, I suppose. But this is just like a tiny little cutout. So what do we do about that? I really wanted to show you our first image that is literally from like a few days ago, but it is somewhat embargoed. And so I'll just mention that this is a huge news, because for a little while we have been already thinking, well, we do need single dish observations. What are we going to do? And if I now recollect properly, sometime last year, Ettore Caretti has led a proposal to use parks exactly for that. And as it turns out, his team has got approved for a pilot observations before the full survey is approved. And so they did observe a little bit of the galactic plane. The thing is that we haven't heard anything up until literally, I think, Monday this week, when they showed, look, this is the parks observations and the Emu possum data from the pilot survey, and this goes under the acronym Pegasus. And it was so spectacular that very much a press release is in the works, and it should be coming in the next couple of weeks. So keep your eye on that, because it is really beautiful. And before I finish up, I'll keep an eye on the clock. I wanted to show you how the fields, the first process fields of the Emu full survey look like. I tried to use here a color scheme so that it will show you the wealth of detected sources and the diffuse emission. These are still unreleased observations. They're just because we need to validate that and then check the quality before they are released. And so this is just the kind of a quick look at some of the cutouts very much. And this is another one. I think it's from the same 30 square degree field. So it has started. We are all extremely excited about that. I hope that I showed you how powerful Emu is, but also how how much more beautiful results of this will be when we have a multi-wavelength or different telescopes, radio telescopes connected, merged together from the different surveys. And just a couple of last slides to highlight that the Emu collaboration actually is very much open collaboration. If anyone from the audience would like to join, it is very much just need to do is join the PI. A lot of data is already public, can be used by anyone, but within the Emu collaboration, what we actually so what is available is very much the raw that comes from the raw images, let's say that way, that come from the ASCAP. But what we do in the Emu, we provide a valued added data as well as the combined images and so on and so forth. So the data are much better. We have a web presence on these 2 locations, and I just kind of highlight that the exec team, that's 2 people that are based in Australia, Andrew Hopkins and Tessa Bernstrom, PI and project scientist. And you had 2 people at NRAO, and myself and Josh. And it is NRAO because we started off working on this survey back when we were in Australia in our temporary positions, and we just kept on stayed. RACS, there is one more thing that you may hear of, that's RACS. This is Rapid ASCAP Continuum Survey. This is not quite Emu, but if anyone is interested, I just figured I'll show it's out there. It was a quick scan of the southern sky and up until +30. The idea is that they'll go through all 3 bands. The first band was centered at 888 megahertz, and then 2 more are coming. But that's very much the survey. I think they only integrate for around 15 minutes on each direction of the sky, while what Emu does is 10 hours, and that's why RACS is with hundreds of microjanskis per beam sensitivity, while Emu is much deeper, or going to 20 microjanskis per beam. But it's out there. If anyone is interested, please have a look. And as my last slide, please let me acknowledge the Wajari Yamati people as the traditional owners of the Murchison Radio Observatory site, where the ASCAP is based. And very much the whole legend of Emu in the sky really comes from the Aboriginal legends, and this is roughly where they would be seen when they looked up the sky. That's where the Emu would be said to be. It was the black spots in the galactic plane, and this is one of these beautiful artworks recently commissioned for the ASCAP surveys. And that's it. Thank you for your attention.
Okay, thank you very much, Anna. That was a fantastic talk, and honestly a beautiful way to end with the commissioning of that artwork. That's a fantastic contribution back to the community. So at this time, we'll open it up for questions from the audience. So feel free to raise your hand or unmute yourselves. And if you want, you can also type your questions into the chat. But while people mull over what they want to ask, I'll start things off by asking very broadly. So how is the SKA going to change things for you?
For me personally, in my science?
Yeah.
And you mean the SKA that is being now constructed, or
yes,
the Pathfinder?
exactly.
Honestly, with the SKA, it's been it's a tough question to answer, because it's been really long years of the discussions, and eventually I think a lot of us kind of said, is it ever going to happen? But so actually my plans detached very much from the SKA itself, and rather I focus on the pathfinders as well as our NGVLA, which I think will come into existence much sooner. They are, of course, NGVLA and SKA may slightly overlap in the lower end of the NGVLA coverage, but otherwise they are separate, especially the NGVLA go to much higher frequencies. But yeah, I'm sorry. My answer, I think, is that I'd rather am looking forward to the full results of the pathfinders like Meerkat and ASCAP, and in the kind of midterm future NGVLA. As for SKA, we'll keep seeing how things are going.
That's a perfectly valid answer.
But how
right.
it changes my science is, I hope that I kind of showed. I'm Radio Galaxy person, Radio AGN person,
Right.
so I'm super excited to see things like that, and actually having this and Villas or any high resolution is absolutely the best thing I can have for my science personally.
Okay, well, let's quickly switch. Jay, go ahead and ask a question.
Yeah, very interesting talk. It's really great to see things come out of ASCAP after such a long gestation. Would you say something? Would you say a little bit more about the potential role of the GBT in this research?
So yes. So what I was actually thinking initially when I was planning on giving this talk is exactly this, that, you do need the single dish observations. And that was unbeknownst to me that this got partially approved from the parks. So, and then GBT, I did check, GBT goes to really nice low elevations as well. Sorry, elevations, low declinations as well. So while it would not, cover the whole emu, it would have a similar overlap with emu as the Villas has. And that was sort of that I started thinking, well, okay, we can try GBT, we can try parks, but that is definitely something that is much needed.
And specifically, this would be 910 megahertz continuum mapping.
No, so no, actually not necessarily. So this particular one, I think this particular example here comes from early science, and we were still sort of finding out which is the best frequency to target for the full survey, and then we decided later that it was 943. This particular one that I'm referring here, the pilot that I saw a couple of days ago as the first image that came at 1.3 gigahertz.
Oh, okay.
Yeah, so there's always this possibility. So Emu gives 943, so it will go from 800 to 1.1 gigahertz, and that is our main survey, but there are other surveys going on ASCAP. For example, Wallaby, which is they are really interested in H1, but they will have a continuum as well, and they are looking at they approved for band 2, which would be around 1.4 gigahertz. And while basically we want to have that data eventually, but they are not officially part of EMU. But if we get them, we will use that, so we will have those two bands coverage. So it could be anything out of that.
Okay, thank you.
All right, thank you, Jay. Any other questions from the audience? Again, feel free to unmute yourselves if you have something that you wish to ask. Seems we have a really shy audience today. That's okay. But Anna, did you have anything else that you wanted to share with us? An extra slide that you were worried wouldn't make it into your presentation?
No. I had to, like, literally, I actually wanted to show you this one, but I took it out just because of the sort of semi-embargo for the press release. So I'm so sorry I cannot show you that, but it should come out shortly, sometime in December. So please keep an eye on that. And then you see the whole power. Well, of course, you're pretty much aware, I guess, how powerful this your spacing is, and how much better this can look like. But so it's still spectacular to see. So.
All right. Well, definitely looking forward to it, especially since you built up the suspense.
Good.
So with that, unless there's one last question that someone would like to ask, but if not, hopefully you all know how to get in touch with Anna. So let's give one final virtual round of applause. Thank you to Anna Kapinska for joining us today. It's been an absolute pleasure.
Thank you for coming and listening.
Yep. All right. With that, take care, everybody.